record on the cloud. Okay.
So now it is getting recorded. So you can probably start it later, means when you start your session.
Okay, shall I start it later? I'll pause that. I am going to deal. Okay, so I'm sharing my screen and I hope you can see the whiteboard now. Right?
Yes, it's visible. It's visible.
Okay. Right. So what we are trying to do now, we are trying to understand the basic idea of boosting, right? Okay. So, and is the writing visible? You can just tell me.
Yes, it is visible.
Great. So you have already been taught bagging. So I assume that we can go straight to boosting, right? And in boosting, we are saying that we are having a classified set to 0. So what we are doing is we are writing down the steps now of boosting, and then we'll make sense out of those steps, right? So first of all, we need to understand the notation behind this boosting. So this f of x, you would have studied in class 11, this is a function, right? And when I say sf cap x, this is an estimate. So any estimate of function. So just to get this notation right, because the standard textbook is going to use this notation, say your fx is a0 plus a1 x1 plus a2 x2. This is a function of x, and x is a vector here. So this x actually, say I'll put it in a capital X sense. So x is basically x1 x2. It is having two variables. So this is a bivariate distribution we might be having. So I am saying this function of x, which is having two variables x1 and x2, has a linear form fx. And when I say f cap x, what does it mean? It means that I have estimated the parameters. So I write a0 cap plus a1 cap x1 plus a2 cap x2. What does it mean? I know the value of a0 estimated from the data. A1 I know and a2 I know. Fine. So we call this as the parameter vector theta, and this is given by a0, a1 and a2, right? And this, after the estimation, theta is the estimated parameters, and this is given by a0 cap, a1 cap and a2 cap. For example, say this was a function which is an unknown function, for which the parameter estimation has not been done. After the estimation, the estimated parameter and the function looks like 3 plus 4x1 plus 5x2. This comes from some estimation procedure using data, right? So my theta cap, which is the estimated parameters, are 3, 4 and 5. Agreed? Is this part clear to you?
Yes.
Right. So whenever we will be using the theta vector, this theta vector, it will be a vector of the parameters. Whenever I'm using the theta cap, it will be the vector of the estimates. Now, any function, whether it's a neural net or whether it's a support vector machine or whether it's a decision tree, whatever you have can be seen to be as if it's an unknown function, right? An unknown function, I do not know the function, and we are trying to find this unknown function here out, and most of these methods come under the class of a function approximation. So what am I saying with this function approximation? What I'm saying is that I do not know the function, but I'm trying to approximate the function using a data and some estimation procedure. So in this case, the function approximation for y x1 and x2. Some data is given here, say 10, 5, 7, 20. I'm just arbitrarily putting some data, right? So I need to have y is a function of x1 and x2, which is the function, assuming it's a linear function. So I put this fx as the linear function, right? This fx, and after the estimation, maybe, just maybe, this is the kind of output I get. So I say this is my function approx, right? This is what is we are trying to do using any either an econometric model or a machine learning model, right? So whenever we say f cap x, it is my estimated function. That's the known parameters. That is, this we are dealing with theta cap with a functional form. So two keywords to be remembered. With an unknown function, if I want to estimate, first of all, I need to specify the functional form. That means, is the functional form linear? In this case, I change the color so that in this case, this functional form is linear in the example I am giving you, right? And then the unknown function has to be estimated using some estimation procedure. Okay, so we know the symbol. Now let's move on. Any questions from this part? Would you like to
One,
ask anything? Please
no,
ask.
I have one request. Could you also explain backing part?
You want the backing to be explained again?
Yeah, quickly.
Okay, I'll explain the bagging procedure once and then I'll move to the boosting procedure. Okay. Okay, just give me a minute. So any doubts from this? Okay, no doubts, so I'll remove it. Okay. Okay, so let's move to bagging, right? So you remember what is a tree? Okay, so let me just do something on a decision tree, a bit of it, so that again we can come back to bagging since you have asked this question. So first of all, we are going to say a decision tree, and we said a decision tree looks something like this, right? So this is this is greater than 30 as one condition, less than 30 as one condition. So this is for x1. So assuming we have three variables x1, x2, x3, and the dependent variable y. Fine, right? So this is the first split which has happened. This is the first split which has happened. The condition is if it is less than 30 or greater than 30, we are saying it is the data set is being broken into two types. Agreed? This splitting idea is clear to you?
Yes.
Okay. So now which variable was used for the first split? X1 was used for the first split. X1 was used for the first split. And what was the value at which the split was made? 30 was the value at which the split was made. Agreed?
Yes.
Okay. So I'll just put it down this way. So say the classic example is the kind of salary a baseball player is getting. Fine, this is the classic textbook example, and this is the number of years of experience. This is my x1. So I'm saying this is some kind of a salary distribution. Okay, and we say that the best split was obtained here at 30, right? So 30 splits this zone into in an optimal way such that the MSE for both the zones, some of the MSEs for both the zones is the least. That's the idea, right? So this is the first split using X1. Maybe after that, the second split is happening at the number of hits. So again, I use salary, right? And already I have two zones which are available with me. Right? Okay, say this was 30. We have done this. So now on this, I am going to further split. So this is zone 1, this is zone 2, and I am going to further split this into more zones. So I don't use this variable. Maybe some other variable at some other value would do better, right? So let me, as of now, try to split it. Okay. So assume that this line, this red line does not exist anymore. It's a dotted line, right? Now I say I either split this zone or I split this zone. Okay. And if that is the case, I'll try to draw a graph now in which on one side I'll say years of experience, right? And on the other side, I am going to say hits, number of hits the person has made. And on this, I'll superimpose salary as a variable. Maybe something like this comes, right? So years of experience was 30, and the this crosses our salary, right? And years of experience, right, is 30 as we saw. And we are saying that which variable now should enter the equation. Say we find out the hits greater than or less than 25 is what, or greater than or less than 25 is what really makes the difference. So 25 hits. Now we have zone number 1, we have zone number 2, we have zone number 3. So we have now got 3 zones out of this data, right? So now this part is less than 30. This guy is less than 30. The zone Z1 and Z2 are less than 30. So less than 30, the split is happening for greater than 25 and less than 25, right? This is clear to you? Is this discussion clear to you? Did you follow this out?
Yes.
So the second split is happening at, so the variable x2 at 25, and the variable x2 is number of hits. Agreed?
Yes.
Okay, now if that is the case, so maybe this would be the third split, and we some other variable at some other value will be causing the third split to happen. So we can continue to do what we call as grow the decision tree. The decision tree will keep on growing, right?
Okay. Okay. So these groups are called bags. Okay?
I'm sorry, can you come again?
No, I'm just asking. So this grouping is called bagging, as in
No,
splitting of the nodes.
no, splitting is not called as bagging. This is called growing the decision tree, right?
Okay.
So I'll just
Yeah.
show you growing the decision tree. Let me rub some part off. Okay. Have you been taught what is the optimal number of splits in a decision tree? How do you control the growth of the decision tree? I mean, how do you know where to stop in a decision tree?
So when there is no the
there are less number of events left.
Right. So
less
I'm growing the
than
decision tree, as you can see, right? This is growing the decision tree. Yes, no.
yes.
It can keep on growing. The decision tree can keep on growing, and I need to have a stopping criteria. Stopping criteria, and if the one criteria is stopping criterion, so I'll say I will stop at this. I'll stop at this, and I will not let the decision tree grow beyond the point, and this is called as pruning the decision tree. Okay, so this is called as tree pruning, right? So this is something I believe has been done, so I'm not getting into that. So I'll start from here. That decision tree keeps on growing till I don't apply a stopping criteria. Generally, a stopping criteria is that in each zone, the number of sample points should be greater or equal to 5. This is what we call as a thumb rule. Right? This is not a statistical rule. This is just a thumb rule. So every zone should have at least 5 points. If I have achieved 5 points in a zone, I will not split it further. Did you get it? Are you with me?
Yes.
Okay, so far so good. So if that is the case, so the splitting criteria, uh, we have already said what is the splitting criteria. The splitting criteria is we are trying to use MSE, we are trying to minimize the errors, and we are trying to have a mechanism in which the sum of the errors of all the zones, all the nodes are east, right? Error being measured through MSE or RMS, any of these. So we have some tree pruning mechanism, and sample size has to be 5 or more, and the moment it touches 5, I don't split the zone further. So far so good. Okay, now I'm going to deal with something called as a decision tree, right? So I'm going to change the word and I'm going to use something called STUMP, stump, and we'll understand what is this stump all about, right? And from here we are going to take it forward. Okay, so any questions from what we have done so far on from this part? You understood that there has to be a stopping criteria, and that we need to stop the growth of the trees, and this process is called as the tree pruning, right? Now we are learning what is this stump business. Decision tree stump. Okay, I'll drop the whole thing off. Let me draw it and explain. So we have a decision tree. We have split it at using variable experience, and the number of years of experience is 25. Less than 25 and greater than 25. This is less than 25 years, and this is greater than equal to 25 years. When you have a single split, right, in a decision tree, this is called as a decision tree stump. Is it okay? Is it understood? So
Yes.
what's a decision tree stump? A decision tree stump is a single split on a single variable using some value for a decision tree. Okay. Any questions on this?
So stump is the first instance, or I mean, could we have multiple?
Just the
stumps?
first instance, the first split.
The first split is stump.
Just the first split is the decision tree stump. Okay. So like this is a tree. Say this is a tree, right? And you cut it at this level. This part is called as a stump of a tree, right?
Yes.
From here we have borrowed the word stump.
Okay.
So this is how we have used the word decision tree stump. So this part is called as the decision tree stump. This part which I am sort of shading. So I cut the tree here, and this is my decision tree stump. So far so good. So I'll move on, right? Any questions? Anything you want to ask me? The decision tree stump is clear to you, right?
Yes.
Perfect. Okay, so let's take the discussion further. So we now know what's a decision tree stump. Okay, so assuming that we are having multiple decision trees. So we have decision tree number 1, and we have fit a decision tree on a model, right? And we are calling the decision tree which we have fit as fx, right? So I'm going to draw something, and let us be clear on this concept. This is the first split, this is the second split, this is the third split. After the split happens here, say, then the split happens here, and this happens here. Is this a decision tree? Yes or no?
Yes.
It's a decision tree. So once I know the structure of the decision tree, if I know the structure of the decision tree, then I'll say this is fx cap. Why? Because I've estimated the structure of the decision tree. So is the difference between fx and fx cap for a decision tree clear to you?
So fx cap is for the known structure.
So I know the structure.
Okay.
As I said in the initial slide, As I said in the initial slide, if I know the functional, I know the function, the estimate of the function is known to me. In that case, I'll call it fx cap. So I am calling it fx cap because in this case, I know this is how the decision tree looks like. So I know it splits at 25, then it splits at say 100, all which variable and the level or the value, either the level of the value depending on categorical or continuous is known to me, right? I know which variable is used to split and at what level is the split happening or what value the split is happening. Then I know the complete structure of the decision tree. Then I'm going to call it as fx cap. Is this clear to you?
Yes.
Right? Any questions? So fx cap for a decision tree must be clear to you, right? So that you tomorrow go back and look at any tutorial on any textbook. You should not get confused that why is fx cap coming for a decision tree. Decision tree is not having a functional form like fx equal to a0 plus a1 x1 plus a2 x2. No, it does not matter. Any function, even this is a kind of a function. The moment I know the structure, if I know the structure for this kind of a function, I could have said that a0 cap, a1 cap x1 plus a2 cap x2, and I know a0 is 3, as I said in my example, this is 4 and this is 5. So I know the structure of the linear model. In this case, I know at what level and for which variables the split is happening. So I know the structure of the decision tree. Are you with me? If I know the structure of decision tree, that means I know which variable is used to split and at what level the splitting is happening. So I am saying this function structure is known and I'm going to call it fx cap. Okay. Any questions? Anything you would like to ask me? Is fx cap clear for a decision tree? Can I move on?
Yes, yes.
Perfect. Okay, let's move on. Okay, now let's take it one step ahead. Okay, so taking it one step ahead, this is the full data with me, right? I'm leading to bagging and boosting only. Fine, since you asked bagging, I'm going to touch upon bagging and from there moving on to boosting. Okay, so this is the full data and I'm going to say this part is my train data and this part is my tester data. That is what you already know, right?
Yes.
Perfect. Now, what do you do in general? You build the model here and you see some kind of an error definition here. Agreed?
Yes.
Okay. Now, let's take this ahead. But you have broken this into two parts as of now so far, right? Always a train and a test. Let's take it a step ahead. And you'll stop and ask me questions, right? Anything which is not clear to you. Let us take this one step ahead now. Let us say we will now like to break this into multiple training data sets. So I have one train data set, second train data set, third train data set, fourth train data set, and this is my tester data. So this is training data 1, training data 2, training data 3, training data 4. So I've broken it into 5 parts and the first 4 I'm calling as training data and the fifth one I'm going to call as the tester data. Agreed? Yes?
Yes.
Okay. So fit a decision tree here. Decision tree 1. I fit a decision tree 1 here. And because I know the structure of decision tree 1, I'm going to call it F. Let me call it capital X because X is having say 5 variables, X1, X2, X3, X4, X5, right? 5 variables are there in this. And I'm going to put a cap. Why am I putting a cap? Because I know the structure of the decision tree. I've estimated a decision tree on training data 1. Similarly, I estimate the structure of the decision tree on training data 2. Similarly, I estimate the structure of decision tree on training data 3. Similarly, I do it for training data 4. So how many decision trees I have?
4.
Perfect. We have 4 decision trees, right? Now I'm going to call this as f cap x1. This guy I'm going to call it, and you must remember this notation. This is used in a standard textbook. Fx3, and this is fx. So we have now 4 decision trees which we have agreed, right? So I have run 4 of these on the 4 parts of the train data, which I broke the full train data into. Okay. And then what do? I say I do something like averaging them out. Okay. So once I do average that out, how do I average that out? I say my prediction, which is now f of average of the full data. I mean, this is what I'm going to use. This part I'm going to use. And this is given by, I take the first decision tree which I have built plus the second decision tree which I have built plus the third decision tree which I have built plus the fourth decision tree which I have built, right? Sum them out and divide it by how many of them are there? 4. Agreed? Are you with me? So,
Okay, so but this would be like the cutoffs for the splits, right? Because we don't have any equation for decision tree, right?
no, we don't have. We just don't have any equation for a decision tree.
But
This,
this averaging, so cutoffs would be the ones that will be averaged.
so let us see what is it that we are doing an averaging on. So once I have done the structure of the decision tree, I put this in the test data and see how well I am doing. I get the error. Yes, I have got some predicted values from this decision tree, right? So the moment I know the decision tree structure, the first decision tree, this is going to give me some predicted values. Yes or no?
Yes.
Yes. So let us take a simple decision tree stum to understand these predicted values. So I'll write here, I'll change the color so that this concept is clear. I said the first split is happening at 25, right? So this is greater than equal to 25 and this is less than 25. Some person who is, so this is your data. So x1 is given as 20. What would the value of and you're separating this into 2 classes. The class is, so on the training data you have learned the structure of the tree. On the test data you don't have the structure of the dependent variable known, right? So y is not, as of now we are going to check it out for the test data, right? So what is my predicted value? My predicted value is, if it is 20 and the classes are 0, the classes are 0 and 1, that is 0 being low and 1 being high, right? So less than 25 is one category, greater than 25 is the second category, right? So you have broken this whole data into, using only a single stump of the decision tree, you would have broken the whole thing into a 0 and 1. So the moment it is 20, you're predicting it to be 0. So the first decision tree stump is going to give you a predicted value as in 0, 0, 1, 1, 0, and so on. Say 0, 21, and this is 26, so it is going to give you 1. So 0, 0, 1. This is just a decision tree stump. It is only using one variable, and your actual values can be 0, 1, 1. So 0, 0. This is true or false? True.
True.
0, 1.
False.
False. And what about this? True. So you can calculate an error definition based on this. Yes or no?
Yes.
Yes. So that means, let's come back to f1x is going to give you some predicted values. Similarly, f2x cap is going to give you some predicted values. Similarly, F3 cap is going to give you some predicted values, dot, dot, dot. So similarly, F4 cap is also going to give you some predicted values. Agreed? So you are going to get predicted values based on all the four. Are you with me? Yes or no?
Yes.
Yes. Now see what I'm saying. Okay, I'll rub some part off. Up to here, if there is any doubt, ask me. So we have understood what is a decision tree structure. We have understood what is a decision tree stump. I am doing an example. This 01 is for a this is a classification problem because we have only two classes. So this is called as a classification tree, right? So dependent variable is of a categorical type. Now what we are saying, this guy is, so if we have a classification tree, so for the first value, you are predicting 0. By the first case, you are predicting 0. Second guy says 1. Third guy says 1. And fourth guy says 1. What is your prediction? One is saying 0 and other three decision trees are saying 1, 1, 1 on the four parts to the training data. Then, because we cannot average this out, right? Because this is a classification problem. So we go, right. So we go by a method called as the and remember this, it's a simple panchayat mechanism. Go for a majority voting. So since we have 0, 1, 1, 1, what is the majority? How many people are saying 1?
0, 0.
3 people are saying 1 and 1 person is saying 0. So what will be your prediction when you are using 4 of these decision tree stumps? 1.
1.
You got the idea of how 1 is coming?
Yes.
Pakka sure? Everyone is clear on this?
Yeah.
Okay. Any questions? So you get a value of 1, but for the test data, you have, so you get a predicted value of 1. How does it come? Majority voting. Actual value is also 1. So you are perfectly doing well on the row number 1. Right? And you can keep on doing it for all the rows, and thereby you are going to get an error of using multiple stumps using a majority voting on the test data. Error on the test data. I'll repeat this. So I'm going to combine multiple decision trees. Once the problem is of a classification type, when the decision trees are classification trees, I'm going to combine them. I'm going to predict all the decision tree values on the test data. I'm going to go by the majority voting, take the majority vote, and row by row, I'm going to predict. In this case, I predict, for an example, I show you how to predict for the row 1. And when I get all the rows predicted, I get an error on the test data. So far, so good. Any questions on this? Is this clear to you?
Yes.
Okay. So I'll rub something off and I'll do the same thing for the regression problem, right? So I'm going to do some similarly something for the regression trees. So no more classification trees. My dependent variable is no more a 0, 1 dependent variable. My dependent variable is now of the type continuous. So now I'll just rub this part also off. The predicted values and the y values won't be like this. Your predicted values are say 5.1, 3.2, something like that it comes, right? So I am going to deal with this in a minute. And let me show this first. This is a decision tree stuff. Please pay attention, right? And ask me a question. So what was my cutoff? I said 25, right? 25 as in the variable used is years of experience. And the dependent variable is salary. So using 25, I have cut off the whole salary data into two zones, Z1 and Z2. This is done using the decision tree 1. Once I've learned the structure, this will be called as F1x. But remember, this is just a decision tree stump. I've used only one variable and only one value. Agreed? So far, so good. And you're clear up to here? Hello? Are you guys there with me?
Yes, yes.
Yes.
So now, if the value is less than 25, what should be the predicted value? This is a question I'm asking you, and this is what we'll try to answer. I had done for the classification case, I had done the majority voting, I am doing the regression case, and I'm asking you what should be the value. No. Okay. So less than 25, this guy, let me change the color. This guy, what should be the value? So I am saying, what is the value of salary given years of experience is less than 25, right? This is the question I'm asking. So what do? I calculate the expected value. This is what I do. So it's basically, in layman's word, I'm calculating the mean of salary such that the years of experience is less than 25. So I take all these points, all say these 4 points, and I calculate the mean. Right? Say the mean comes out to be, so the salary value mean comes out to be 110 units, right? 110 in some units. So let's now understand this. So a person who is getting a salary of 20, how much does he earn? 110 units. A person who is getting, say, 23, how much does he earn? Again 110. So why? Because anything which is less than 25, I am predicting the conditional mean of salary for which the years of experience is less than 25, and that comes out to be 110. Is it okay? Did you follow this? Yes?
Yes.
Okay. So far, so good. And for Z2, I am saying the expected value of salary such that the years of experience is greater than 25. That means I'm calculating the mean of salary such that the years of experience is greater than 25. So the mean of these 2 points, say, comes out to be 115. So what would be, so say this is 29. What would be the predicted value of salary when the years of experience is 29? What should I write here?
115.
Correct. Very good. 150. So that's it. That's my simple logic. What am I going to take as a predicted values? The predicted values are the zone means. Remember this. Do remember this, please. So predicted values are the means of the zones. Zone mean is the predicted value. Is it okay? This is clear to you? Yes?
Yes. Yes.
So for the decision tree 1, the zone means are coming as 110 and 50, 115. Say for the second decision tree 2. So I'm going to change decision tree 2, fx2. The predicted values come out to be 105 and 120. So I fit a second decision tree because the training data has changed now. So decision tree structure will also change now. Yes? Training data change, okay, decision tree will also change. So for the second decision tree, these are my zone means. Similarly, for the third decision tree, I could have the means as 120 and 130. right? And similarly for the fourth decision tree, my zone means will keep on changing and the cutoff will also keep on changing, right? So you will now get four different values. You'll get four different values for each of the decision tree. So now I'm going to rub it off and I'm going to
So
write.
one very basic questions.
Yes, please.
These four decision trees which we have taken. So the sample data, I mean the train data, are they in proportion? I mean, or these are just random four samples?
So I divided this into 20%, 20%, 20%, 20%, and 20%.
No, but then weightage by variables I'm saying. So let's say we have up to two independent variables A and B. So with ratio 2:1 in an overall, I mean, overall sample, from which we took 2:1 ratio for this train set and 2:1 in test set. But then when we divide this train set, so will that 2:1 remain for this TR1, 2, 3, 4? Or I mean, they are just the random four sample, just 20% of population. The ratio could be anything.
So whenever you are fitting multiple decision trees for a bagging purpose, or when you are fitting it into in a boosting algorithm, you will have equally weighted training data sets.
Okay.
Otherwise, you have to bring in W1 here in this equation, W1 multiplied by the fx, which I am not doing because all of them are equally weighted.
Okay, they are equally weighted.
Okay.
Then even if they are not, so you're saying that we do have a formula for that.
Right, because they're equally weighted, so I don't have to multiply them with W1, W2, W3, W4, and so on.
Okay.
I can very well just take them as equally weighted and go ahead.
Okay, thanks.
Okay, any other questions? So let's say now we are getting for all the decision trees, we have got all the decision trees terms, and we have a value of X, which is the number of years of experience, right? And the years of experience is, say, as I said, 25. The first decision tree is giving me, decision tree 1 is going to give me predicted value of 100, as I said, 110. Second decision tree 2 is going to give me the predicted value of 105. So 25 and less, let's say, is the cutoff. And the decision tree 3 is going to give me a value of 120, and say decision tree 4 is going to give me a value of again 100 and just 100. Okay, we have got four values from four decision trees based on the training data 1, training data 2, training data 3, and training data 4. So what is my predicted value? This is the equation which we have set. We'll just take them, all of them, and we are going to take an average. So it's 105 plus 110 plus 120 plus 100 divided by 4. This is my overall predicted value. Agreed? Did you follow this out? Yes or no?
Is it predicted for X less than 25 or?
So it is only for predicted for the value of X is, where X value is 25.
Okay, for X.
For each row, you are going to have a predicted value. So predicted value for row number 1. So as to avoid confusion, let me not write 25. Let me use 20. 20 is less than 25. So anything less than 25, we are going to use zone 1 mean. Okay. This zone 1 mean. This is the zone 1 mean we are using. And because we are using the zone 1 mean, 4 decision trees gives 4 different means for the zone 1. And I am going to get these 4 different values. And this is the predicted value. Agreed?
Yes.
Now, so what is the steps which we have taken? We have step number 1, broken the whole data set into multiple trained data sets and one test data set. Okay. And then we have taken the learned structure. I'm using this word learned, and you need to remember this word learned structure of the decision tree. That is DT1, DT2, DT3, and DT4. And using this learned structure of decision trees, I'm going to create an average out of all of them. This method, and that will be my predicted value. This is my predicted value, and this method is called as bagging. Right? So we have done the bagging. Okay. Any questions on this? You understood what is bagging? Are you clear on this? Anything you want to ask me on bagging? Hi guys. Is it sure clear? Can I move on?
Yes.
Okay, so let me write down the general equation for it and let me close this and move on to boosting. Okay. So how many training data sets did I break this up into in this case?
4.
4. Assume that I do it for large number of training data sets. My data set actually is a very big data set. So I don't like just 4 of them. I can do it for B of them. So if I try to break the data into B data sets, right? So how many classifiers I'm going to use? That is how many decision trees I'm going to learn. F1. Okay. The first decision tree, the second decision tree, dot 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 dot. How many of them would be there? The BF decision tree. Because we have broken up into B data sets, and these B data sets are what data sets? These B data sets are the trained data sets. So I've got B of these decision trees. Once I've learned the structure, so they would be called as F1 cap, F2 cap X, dot 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 FB cap. So these are learned decision trees. And what would bagging do? Bagging is going to take all of them together, summation of F of B X, and this B goes from 1 to B and divided by B. This is going to be my prediction. Or in other words, average of X. Is this clear to you? Is this expression clear to you? This is a classic textbook expression which you will find. So what is this doing? This chota b, the small b goes from 1 to b. That means f1b plus f2b plus f3b all the way to f capital B X divided by b. That's it. There's an average of all the decision trees. This is exactly what we did here. Did you follow this out? Is bagging clear to you? Can I move on?
Yes, I have a little confusion, not
Please
sure
ask.
why it's cropped up, but then we've took 4 or let's say B number of decision trees, and they are in equal proportion, and then we run them, we took average and we fit them into this equation and we get our prediction. But
Yes.
then I mean, and also they are following the same structure, right? I mean, so they all have a cutoff of 25. But
No,
then
they may not have a cutoff of 25 actually. They will have different cutoffs, and even the variables which are used can be different.
okay, okay, so they can have different cutoffs. So yeah, I mean this actually solved my question. So my question was if the
So
cutoff is
in
same, so
general,
why
the
do we have
decision
to
trees,
divide them then?
right? So in general, the first, okay, let me write it somewhere here. Okay, I'll erase a bit of it and I'll write down here. In general, just take two examples, two decision tree stumps. The first decision tree stump is, as you said, 25, greater than equal to 25 and less than 25 years of experience. This is the first decision tree stump. Okay. The second decision tree stump is the cutoff is happening at 18 years, greater than equal to 18 years for the second training data, this guy is coming from here, right?
And is
And
it always have to be the same variable? Only the cutoff
no,
could be different.
no, may not be. Now the third decision tree stump is number of hits.
Okay.
Hits is greater than 50, equal to 50, and this is hits less than 50. So you will see that the cutoff is different and the variable is also different.
And obviously, I mean, there could be more iteration to that. So, for example, after in the first one, if we say greater than equals to 25 years, then we can have more branches to it.
Yeah, but we are not using so
this
as I said,
we are not using, but then there could be.
There could be. You can just have a large decision tree. I
Okay.
used a decision tree stump. You could have learned a tree for a very large growth, and then you could have used 4 different or B different decision trees, and
It
you
could
could
be
have
mutually
made a
distinct in every perspective, right?
yes. So in the decision tree 1 is completely different in structure from the decision tree 2 is completely different in structure from the decision tree 3 and 4 and so on.
Okay. Okay. Yeah, makes sense. Thanks.
So if you ask me to summarize this bagging in 2 lines, one, you would go for repeat train data, and that is break the whole data set into multiple train data, and then fit B decision trees, average them out, make a prediction, and that is approach is called bagging. In the real world, now this is something which you need to know from a pragmatic and practical perspective. Your data set is not large enough, so you will not be able to break this whole thing like I have shown here, right? So I'm clearing the drawings. The real world could be something like this. This is what your test data and train data looks like. Okay, for the decision tree 1, so it is say 80% and this is 20%. This is randomly chosen. When you do it second time, again you can break it up into a train data and a test data, 80% and 20%, decision tree 2, but this is also randomly chosen. What is the impact of this? This means that this train data is not similar to this train data, because some of them will be similar, some of them will not be similar, and you keep on doing this B times and keep on fitting B decision trees in this. Do you get this point? Because in real world you will not have the luxury of having such a large data set that you will be able to break this into B parts. Training, fine, impossible to get such a large data set. So you will do a random train test breakup, and every time you're going to fit a decision tree on the random train test breakup. Is it okay? Is it clear to you?
Yes.
Okay, so this concludes our the discussion on the bagging. So I'm moving on. You asked me the question, so I clarified it. So I'm moving on to boosting. Some of the syntax and notation is same, so the previous discussion would really help us. Any last call for any last minute questions from your side before I move on to boosting?
I have another one. I mean, again, a conceptual one.
Please ask.
Okay, so we use B number of these combinations. So obviously the discrimination of all these train test combinations or all these, I mean, B data sets would be different. So why do we plan, I mean, why do we decided to use the average of all these and I mean, the bagging method instead of, why can't we pick the one which has the best discrimination?
Okay.
Is it
right.
to avoid the overfitting, or I mean, what could be the reason?
So what happens is, if there is a chance that one by chance you could have got a train data on which the model is built, which is doing very well on the test data, right? But when you really try to resample it and try to fit another decision tree, it gives you a very different result, which is also coming from the same sample.
Yes.
So as to avoid the element of chance, we do repeat sampling. The B part is this reduces the variance. of the prediction. So I want to, when you really go back to your initial lectures, which you would have had the mean versus variance trade-off, right? This is a variance reduction technique. So bagging helps us to reduce the variance of my forecast, of my prediction.
Even
Okay,
if
these are,
we choose to have the we choose to keep the one with highest discrimination, you're saying that
no, we will not choose the one with the highest discrimination. We'll choose
when we'll average all.
as many random samples from the data set, call them the train data, and average that out. We're not leaving anything to chance. It's possible that if I were to use one train data, it's something like this. Look at it this way. You're having a trading strategy in finance, right? It works very nicely for a 6-month period, right?
Okay.
And then you start believing that this trading strategy is really good, but it may not work very nicely for the next 6 months period because the market conditions could have changed.
Okay.
Right? So your decision tree in a similar way can do very well for one train data, may not do very well for the other train data. So I try to check the prediction across repeat samples of train data, and then I average it out so as to give my prediction.
Basically, we want to have multiple scenarios incorporated in our prediction. So maybe at this point, one seems to be the best one out of others. But then you're saying that considering the long-term predictions and I mean the effectiveness, we consider all of them and use this bagging technique to have a robust model.
Right. So what we are saying is, yes, all these scenarios are sort of coming in from the random sampling we are doing for the trained data. So every data characteristic is being captured, and on that we are fitting a decision tree, and then finally we are averaging out the predictions and giving a average prediction, which is called as the bagging. Okay.
Okay.
Any other question? Anybody else would like to ask any question? Okay, let me move on to boosting then. So what I've planned is I'm going to give you the generic idea of a boosting, and we'll do a quick tutorial on Python with one of the variants of boosting called the XGBoost. Fine. So let's see. So we are going to deal with the steps, right? And you now will not have any problems. Why? Because you already know the symbolism. So first of all, we are saying set fx to 0, right? So what is fx cap? What is fx cap? Fx cap is the predicted value. Is it true or false? True, right? So we now know that fx cap is nothing but the estimated decision tree, right? Remember that we said no cap matlab we know the structure of the decision tree.
Yes.
So we are saying the initial prediction of the decision tree is 0. When I say fx cap equal to 0 means my initially the decision tree predicts to be 0. Is it okay? Okay, you'll stop me and ask me question. This is not so simple, right? And it'll take some time to sink in. This is the first thing you are predicting. It's a setting. This is an algorithm we are trying to understand, and we are trying to create a variable called r sub I. So what is this r sub I? We create a variable, right? And we are setting this equal to y sub I. What is y sub I? Y sub I is my dependent variable. Right? So what am I doing? I just understand this part. This part I need to understand. You stop me and ask me. So I have a dependent variable. I means the ith row. So the data set looks like this. So I'm just dealing with 3 variables for my simplicity. This is y, this is x1, this is x2, and this is the ith row, and this ith row is given by y sub I. Agreed? So ith row has a value of y sub I say equal to 10. So y ith is 10. So if y, the first row is 5, so I'll say y1 is 5. If the third row is 10, so I'll say y3 is equal to 10. Is this symbolism clear to you? Is it clear?
Yes.
Okay. So what I've said is, so let me take this ahead. So we know what is y sub I. I is the row index. So my I is the row index, right? So all the row indexes I am matching, and I'm initializing a new variable called ri to be equal to the values of yi row by row. Okay, for all I in the training data. Okay, is this clear to you? Is this clear to you? So what is the initial? So I'll just do a quick true and false to get this idea. What is the initial prediction? 0. True or false? Initial prediction is 0. True or false?
True.
True. And we have created a new variable ri, and we are going to understand the meaning of this ri later on as it comes up. That is initialized. That is initialized to all the elements of y. So R1 is equal to 5 in the initial stage. True or false? Is R1 5 in the step 1? True or false? True. Is R3 10 in the first step? True or false? True. So what is R1? 3. Why? Because we have initialized it to y, row by row, and R number 3 is 10. Why? Because we have just taken the values of y row by row and set it to
R1 is 5.
Ri. Agreed? Okay.
Sorry,
R1 is 5.
Yes.
I've written 3, right? That's a very good sign. R1 is 5. Got it?
Yes.
Perfect. Okay. Now what we are doing, we are fitting a tree. So we are fitting tree. Okay. And how many trees do we want to fit? So this is a fitted tree. This cap means learned. Right?
I'm trying to absorb. I mean, when you say that fx equals to 0, it's initial prediction.
Initial prediction is 0. Perfect.
So what do we mean by that? I mean, initial prediction is 0. So are we saying that we do not know or we don't have any variables, and then we?
So initial prediction is 0 is my decision tree does not have any fixed structure. That's it. I don't know much about it. I'm just arbitrarily putting the value of 0. It as 0.
So then why do we have this f cap if we don't know the structure?
I am saying I'm assuming a decision tree structure which will keep on updating with iteration, and the initialization of the structure is 0.
So shouldn't we write that fx equals to 0 instead of f cap x?
So if fx equal to 0, that will be meaning in a variable sense. Are you with me? So I am saying there is a learned decision tree structure which I'm calling it to be 0. Who is calling it? I am calling it. Right? How do I know it? I'm just calling it. And I'll keep on improving this structure every time I move in the iteration. So there's a loop I'm going to put in. I'm going to put in a loop here. It goes down, down, down. It goes back to the step 1. So finally it will be go to step 1. And every time it goes to step 1, this fx equal to 0 thing will keep on changing later.
Okay.
Right? So the 0 will keep on updating. But as of now, the initialization is that there is some decision tree which gives me the value of 0. That's an initialization.
This is just the initialization you're saying.
Just an initialization. So this is nothing but the initialization step. Okay. Is it okay?
Yes.
Okay. So now fit a tree. So how many trees do you want to fit? Fit B trees. Right? We know that from the previous discussion, f cap chota b x. What does it mean? It means the bth tree. Remember? We discussed this in the bagging class just now. So when I say fit the F cap B, what does it mean? This is the Bth tree. Okay.
Yes.
Are you with me? I am not writing X every time. Understand that there is an X always in that. So even if I write FB, I just write FB, understand that the argument is always there in the decision tree structure. Okay. So far, so good. So far, so good. We have fit how many decision trees we have fit?
B.
B. Okay. B decision trees we have fit. And we are saying that we are going to have each decision tree with D splits. Now, what is the meaning of D splits? So D times you're splitting the decision tree, right? So if D splits are there, so how many terminal nodes will be there? So I'll drop some part off to clarify this, right? Here I'll write. So if I split once, how many terminal nodes are there? 2. Am I right? If I split once, how many nodes are there?
2. 2.
If I split second time, how many terminal nodes are there?
3.
So this is the basic idea we want to understand. So 1, 2, 3. This is already split. So if I split D times, so how many terminal nodes will be there? D plus 1 terminal nodes will be there, and you need to remember this, right? So on what data? Data is your X. Your data is, to make a note in the copy, it will be very good. Fine. Your data is X, means X1, X2. This is my X, right? And the data which you are going to use is R. This I'm going to put a red line and I'll explain this. See this part out. Got it? So you are saying you are fitting this to yi only, but you have taken yi and assigned it to ri. That means you're basically fitting it to y only. But now you are saying yi assigned to ri and you're fitting it to yi by storing the values of yi in a variable called r. Is this clear to you? It's as if you're saying you're fitting it into y only. Agreed or did not agree?
Yeah, agreed, but then
What is the use?
Yeah, but what's the use? So why can't we use y?
I'm going to show you that, right? So far, so good. You're fitting it. Okay. Then let's, okay, just hold on. So we have fitted to yi in a sense by storing that yi in another variable r. Now we move to the next step. So we are saying update. What are you going to update? You are going to update all of these B, F1, F2, FB, all of these B trees. And each, for one instant, it is F chota b, right? All the B trees. That means all B trees, right? And how do I update? I am going to use a method as in an updation rule. So I use an updation rule. Let us understand this updation rule. I first of all use f cap x for any BH tree. So this is the BH tree, f cap x plus a lambda, and understand this idea, a lambda times f. So let me not use b here. Let me use b here only. A lambda, wait, yeah, a lambda, no, it's an eraser. Take the pen, right? A lambda times f b x. Yeah. And this I am going to use to call it as f cap x. So this is my updation rule. So what is the updation rule doing? So what is this part? Let me use a red part. Can you see this red part I'm highlighting? What is this FBX? This is a decision tree which you have learned. Yes or no?
Yes.
I am saying don't take the whole decision tree. Take a part of this decision tree. That means multiply it by a number which is less than 1. Lambda is less than 1. So take a part of this decision tree, add it to the original value of fx. What was the original value of fx? 0. And update the new value of fx. So this, in the first iteration, the fx was initialized to 0. Once you fit the first decision tree, right, the bth decision tree, say, it updated the initialized value of fx. Now the updated value of fx is a lambda times the first decision tree value. Fair enough. So this fx is updated. Then what do? You do another updation rule. The updation rule is on the R update. I'm going to explain it once more. Don't worry. And I'm going to say Ri is also updated. Ri is updated as in the original Ri minus lambda times f of bx cap. So from Ri, I am subtracting that part which is already explained by the decision tree. This is being subtracted from this, and this is a residual which comes here. That means there are two steps which are happening parallelly in two mechanisms of update. The first update is starting from a predicted value of 0. Wait, I'll use a spotlight. The first one is using a predicted value of 0. That predicted value of 0, this is the 0 value here in the first iteration. You are using a decision tree, something is being predicted from the first decision tree, multiply with a number less than 1, right, lambda, and update. So something is coming from the first decision tree, right? Say b is equal to 1, something is coming from the first decision tree. And Ri was initialized to yi. That means the initialization of residual was the whole value of y. From the whole value of y, something is already been predicted. Subtract that part, and what is now not predicted is what we are calling as the residual. So as and when we keep on iterating, what is going to happen? The predicted values will keep on increasing and the residual values will keep on reducing. Are you with me? Okay.
Yes.
Now let us write down the final step now. Right, when to stop, how much time do we need to do it, right? And the final step is you do it for lambda times f chota b x cap, and sum of b goes from 1 to b. That means do capital B times and divide by b. This whole thing is your new predicted value of the decision tree. So what you are doing is you are taking a small value of lambda. You are taking a small part between 0 and 1. That is the weight you are taking, multiplying that with each decision tree values and taking a very small fraction of the output of the decision tree from decision tree 1, then a small fraction from the decision tree 2, then a small fraction from the decision tree 3, and a small fraction from the decision tree 4. Similarly, you're doing it b times, and you are taking an average of all of them, and you are giving a final prediction. So rather than using a equally weighted thing, you are multiplying this from a starting value of 0 as a prediction. You're taking decision tree 1, lambda. What is left out? I repeat, what is left out? You're again running a decision tree on the left out part of the prediction, and again running a decision tree. Then what is left out? You're running a third decision tree. Then what is left out? You're running a fourth decision tree. So your predicted values keep on adding, and what is not predicted keeps on reducing. So as you will find, the residual keeps on decreasing and the actual predicted values keep on increasing. Are you with me?
Yes, but then I have a few questions.
Please
So,
ask.
so if we say that, okay, once we are done with step number 4, so we have some residual value and then again we run the decision tree. So is it that decision tree 2 which will run, or I mean, it will be an average of all decision tree but we run again? So what my
Okay.
question is,
So once you are
we have multiple decision trees in our training data sets now.
right, so
So
we have
during
capital
this-
B decision trees in our training data set.
Yes. So each time all the decision trees would run, I mean, in each iteration, or I mean, there would be like the first the DT1 will run, then we have some residual value, then DT2 would run, again we have some residual value, and then DT3 and so on.
Yes. So first of all, DT1 will run. You'll have a residual value.
Okay.
Then DT2 will run. You'll have a residual value. The residual value will keep on decreasing. Then DT3 will run. There's a residual value and keep on doing it till B times you will run it out.
So then we have a definite answer, like how many iterations do we want? So it means that the number of divisions which we have in our
How
training
much
data set.
is B, right? How many
Yes.
times to fit it? And what should be the value of lambda?
Yes,
Right?
lambda.
Are you with me?
Yes.
Now, to answer these questions, I'm moving on to explain to you what is cross validation. Okay, so 2 questions are unknown as of now, not yet answered, and I'm writing it here. How to choose B? How many times the decision tree has to run? Right? And how to choose lambda? These 2 questions I have not answered, but I'm going to answer them. But assuming there's a B and a lambda, I can run this algorithm. Would you again look at the algorithm and understand how from an initialized value of prediction equal to 0, you run one decision tree, take some lambda multiplier of this, which is a very small value of lambda, take that as a prediction, subtract from the original value of Ri what is predicted and call that as a residual, and keep on doing it B times. Is this algorithm understood?
Yes.
All people in the class? Anybody to whom it is not clear, because I'm moving on now? Okay, I've changed the page. I'll come back to this anytime you want me to. Okay. So these are 2 open questions, we wanted to answer. The first question is how to choose B. What is B? Number of decision trees. How do I really choose it, right? And how to choose lambda? Lambda values, thumb rule is it's between 0.01 to 0.001. This is a thumb rule for lambda. You take some values between this. So we really don't choose anything. Okay. But here is what we need to understand. The method of choosing this B, that is how many decision trees, this is number, right? Number of decision trees to run is by a method called as cross validation. And we'll understand this out. Are you with me? So we're understanding cross validation, and that's it. Once you have understood it, the treatment of boosting is done. Okay. And there are many variants of boosting. Has this been taught so far?
Sorry, what?
Do you want me to teach it or do you know it?
The cross validation, we have idea, but it's good if you can quickly recap.
Okay, I'll do it. Okay, so again, let's say this is my test data and this is my train data. I'm saying I'm breaking this up into 5 parts. This is train data 1, train data 2, train data 3, train data 4, and train data 5. And this is the test data. Is it okay? So this is a basic structural change which I have made in the data. overall data given to me, and I am going to ask a question, which model is better? So I'm going to choose a model. You will stop me and ask me questions, anything which is not clear to you, right? So I am asking a question on model choice. The question is y equal to a0 plus a1x. Take a single variable, right, for ease, versus y equal to a0 plus a1x square. And these two parameters are different, so I'm just putting it a0 dash and a1 dash. Which model does better? How do I answer this question? So what do I do? Understand this. I run these two models. So let me call it M1, let me call it M2 on the train data 1, and I predict it on the test data, right? So for train data 1, I have run the model and I have got the results a0 cap plus a. You stop me and ask me, this is very, very important that this is clear to you, right? A1x for the model 1, and for the model 2, I am getting the value of the same as a1 cap x square. So these are my estimated values. Using this, I am going to calculate the error using the test data, and I'm going to get the MSE values on the test data for the train data 1 for both the models. Are you with me?
Yes.
So I'm going to get the
we know the values of these
parameters. Yeah, because if I have trained it on TR1, I already know the parameter values, right, of these two.
Okay.
Okay.
Yes.
I have fit the data to these two models, and I already know the values of A0, A1. I know the values of A0, A1. I also know the values of A0 dash and A1 dash, because I've used a data to estimate the values.
Yes.
Okay, so all these parameters, these two parameters I know, and these two parameters. Okay, so I find the MSE values for test data for M1 and MSE values for test data for M2. Are you with me so far?
Yes. Yes.
And I'm going to call it MSE for M1, MSE for M2 for the first train data. I'm going to change the color so that there is no confusion. This is for the first training data. Okay. So far, so good.
Yes.
Okay. And you will stop me and ask me a question the moment you are not clear about anything. Similarly, for the train data 2, I am going to get the MSE for model 1 and MSE for the model 2 for the second train data, right?
Yes.
Are you with me?
Yes.
Similarly, I am going to get this for third train data, fourth train data, and fifth train data also, right?
Yes.
So if I want to ask the question, what is the overall MSE for the model 1? What is that? MSE for model 1 for the first train data plus MSE for model 1 for second train data plus MSE for model 1 for the third train data plus MSE for model 1 for the fourth train data plus MSE for model 1 for the fifth train data. This whole thing divided by 5. Got it?
Yes.
Similarly, for MSE for model 2, that will be exactly the same MSE for model 2 for first train data plus dot 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 divided by 5. Exactly the same thing, only M1 rather than M1, it will be M2. Right? You got it?
Yes.
So which model is better? That whose MSE
Is lower.
is lower. So you can choose the model based on this method, and this method is called as cross validation. Because we divided this into 5 parts, this is called as 5-fold cross validation. Agreed? Did you get it?
Yes, yes.
Perfect. So we have understood five-fold cross validation. Now let us answer this question which we had got again. How do we choose the value of B? Right? In this. So let us take B equal to 5 versus B equal to 10. Okay. That value of B, which on in a cross validation sense on the tested data is going to give you a lower value of MSE, that is going to be the choice of B. So you choose two or three B's. So B equal to 10, B equal to 5, B equal to 20.
So is it a
B
random
equal to
choice
15.
or
5, 10, 15, 24. I'm sorry.
so choosing B? I mean, so you're saying that,
Again.
yeah. My question is, so is it a random choice? You're saying that we should pick any, I mean, so any five or, I mean, whatsoever decision trees to run this.
Right. Right. So once you have this bagging and you want to choose B, so you will create B possible values as 5, 10, 15, 20, 30, 50, whatever you want. And this is my choice set. Your
Choice set.
your choice of B is only going to be coming from this choice set based on cross validation. So cross validation is only a relative method to choose the model parameter. Are you with me?
So this choice set, you're saying that before having this choice set, we have to do the cross validation.
No, so first of all, you will give the choice set.
Okay.
So you will say, I will test it for 5, 10, 15, 20, 30, 50. These B values I'm going to test it for. And I'm going to run the bagging. That value of B, which is going to give me the least error for the for the test data, that will be the choice of B.
Okay, fine. I mean, so there would be different B values. I mean, the value for B's, and whosoever has the least MSE, that
right.
is
So
that is the
so
actual
if you
final
run
state.
this, yes. So if you run this iteration, you will do it for B equal to 5 versus B equal to 10. The same 4 steps, right? And you are going to test the prediction on the test data. If B equal to 5 gives you less MSE in a cross validation sense, that means you're breaking it up into 5 parts into train data, some parts into train data, some parts into test data, one part into test data, right? Then that's it. So the B equal to 5 will be what would be used.
And the number of iterations would be ideally. I mean, so like how many sets we should choose first before running the cross validation?
No. So you choose any value of B and calculate the MSE in a cross validation set. Then choose another value of B and calculate the MSE in a cross validation set and keep it till that value of B, which is going to give you the least.
No, but then there has to be a choice, right? I mean, so if we choose if we can have 5 sets or 10 sets or 20 sets, so more sets are better. That means, I mean.
So the moment you keep on increasing the value of B beyond a point, overfitting will happen. Fine. So that will be like putting a ceiling. You cannot choose an infinite number of decision trees because overfitting will start kicking in.
No, but then I mean, there are two things. So one is first we are choosing the set. So in that, I understand that maybe if we have 100 decision trees, so maybe out of that 100, I'll choose 10. Any 10 of decision trees to be in a set. Then I'll choose another set of 10, another set of 10. So how many times I should repeat? I mean, I should how many sets I can have. So are you saying that having more number of decision trees in a set would overfit, or having more number of choice set to arrive at which is the best would overfit? So like if we have this one, let's call it B1. So we can have a B2 with again like 2.
More number of choice has nothing to So more number of choice has nothing to do with the overfitting. Okay. It is the number of trees which.
Okay. Number
So
of
what would
trees
happen
out
is
of the
once you
total
keep on
tree.
increasing the number of trees, so say
Okay.
at, yeah, so at 15, what you will find is after 15, the error increases. So error is going to reduce up to 15, error goes down till 15, and error starts becoming more after 15 because it kicks in. So more values in choice set does not really matter. The thing which really matters is the decision tree numbers cannot go up. Okay.
Okay. And is it like, I mean, if we have more choice sets, so better the result would be, I mean, so we'll get more choices to see, I mean, which of
Yes.
these sets have
So
minimum MSC.
yes. So ideally, you could have started like this 10 decision trees, 11 decision trees, all the way to 500 decision trees. B values can go all the way. And so the software will test for 10 decision trees, then 11 decision trees, and say for 25 decision tree, it will say this is the optimal value for the decision tree. After overfitting starts happening. More
Sorry,
than
your
25.
voice was breaking, but then overfitting, you're saying that if we have more number of decision trees, so why are you choosing the middle values like 15 you've said earlier, now you're saying 25? So that's something which I'm not able to absorb.
So okay. So let me put it this way.
Okay.
So question, is it always true that the middle values will come? Not necessarily, depending on the data set. It is possible that the actual values which are chosen are coming as in say 30. It's possible that this is what is chosen. No, I don't want to the eraser, I want the pen. Just a minute.
Sure.
Okay. This is the value chosen, not necessarily the middle is giving me the optimal value. I have just taken an example, right? Optimal value in terms of MSC, after which the MSC keeps on increasing on the tested data in a cross validation set. That is my optimal value of B. Okay. Did you follow it?
So basically,
Need not be necessarily in the middle. It can be at the initial phase or at the end phase also of the choice set. Depends on what is the structure of the data.
Okay. But what I understood is this B will be one model. So in which we run these 6 decision trees to arrive at one value, and then for that value we see what's our MSC. So am I right or wrong? Or should we compare MSCs between this 5th decision tree, 10th decision tree, 15th decision tree?
Okay, so I'll just erase this thing and clarify this once more.
Sorry, I'm just trying to.
So let us say, can you hear me?
Yes.
So for B equal to 5, you are getting the MSC value
Okay.
for cross validation, yes or no?
Okay, yes.
So for B equal to 10, you are getting an MSC for cross validation.
Okay.
For B equal to 15, you are getting an MSC using cross validation, right? For B equal to 20, you are getting an MSC and use cross validation. Now, which is better? Do it for B equal to 30, MSC cross validation. B equal to 50, get an MSC value, cross validation. Which is the best value? That is, which is the minimum MSC. Say B equal to 30 is giving me the minimum MSC. This is my minimum. So my choice, the answer is B equal to 30. So I am going to predict using 30 decision trees. Did you get it?
So 30 by 30, we mean that these are the number of decision trees, B equals to 30.
B equal to 30 means 30 would be the number of decision trees. Go back
30,
to this algorithm.
Okay, 30 would be the number of decision. What I was thinking is these are the indexes. So
No,
like
no, no,
fifth decision tree and 10th decision tree out of those training samples. Okay.
no.
So
See
these are
this.
the number of decision trees.
No, if you look at this equation, I'm going to change the color to red to clarify this again. If you look at this equation, it is F cap B, and B goes from 1 to capital B. That means how many decision trees are fit here? B decision trees are
B.
fit here, and you are averaging out all of them. Okay.
Okay. Okay. Now I understood.
Okay. Last thing, I'll just come back to this train and test data, right? Now I'll just show one more thing in this train and test data, assuming that there is nothing like permanently trained data or a test data. Assuming this is what you have. See this out. I'm again going back to the five-fold cross validation. How many breakups are there? 1, 2, 3, 4, 5.
Yes.
Okay. I am going to call this guy as the test data. Okay.
Okay.
So far so good. So in the
Yes.
first instance, 4 of them are the trained data, 1 is a test data.
Yes.
Okay. So for, you're clear on this?
Yes. Yes. Yes.
I'm going to change this again and show you the structure of the cross validation once, so that this concept is also not having any confusion. In the second iteration, what would happen is this will be the test data, and the parts, this will be trained, this will be trained, this will be trained, and this will be trained. So the fifth part is the test data. Then the first part is the test data in one iteration in cross validation. Then this is train, this is test, this is train, this is train.
But then the numbers could also differ, right? I mean, so we may not have always 4 trained data sets. We can have 3 or 2.
You can have as many data sets, but for the same cross validation, it has to be consistent, right?
Okay, for
So,
same. Okay. Yes.
so this is a threefold cross validation. And what is happening? This is a five-fold cross validation. I've just done the 3. I'll make the other 2 also, so that there is again no confusion. So test has come here, test has come here, test has come here. So train, wait, train. Now test will come here, train and train. Got it? And one more will be left. I'm going to draw it here. So this is train, this is train, this is train, this is test, and this is train. So you will find that first case, the fifth one, fifth part is the test data, then the first part is the test data, then second part is the test data, then third part is the test data, then fourth part is the test data. The rest of them are train data, which means your definition of test and train keep on rotating, and 4/5 and 1/5 train data, test data keeps on rotating, and you're running the model on the test data by varying the definition of train data. This is five-fold cross validation. Are you with me?
Yes. Yes.
Okay. So any questions from this part? You understood the boosting algorithm?
Yes.
Okay. You understood how the choice of B is made using the cross validation?
Yes.
Okay. And you have understood this is how I just gave you an example of how to do a cross validation choice based on B. Okay.
Yes, but then one thing which I didn't understood is when you've said that 3-4 cross validation, these are the same data sets where
Yes.
we choose that okay
Good.
which, so first the first decision tree, I mean, so we say that okay, this is test and the others are training, then we keep on shuffling these data sets, so consider
We
the
keep on
other.
shuffling, right?
But then how do we decide amongst these 3 that okay which one we should choose? So is it again on the MSC we see that okay where the MSC is lowest when we do I mean when we fit this model on the test data set, or
So the Yeah, so every time we are shuffling it and we are calculating the MSE. So since I have done it 5 times in this case, as you will see, so every time we keep on doing it, we see that the MSE value on the change test data is recorded and averaged out. And for that model for which the MSE is the lowest, that is the model choice.
Basically, even if we take one row, so this is the five-fold cross validation. So basically, what we are testing is TR1 versus TR2 versus TR3 versus TR4.
So what we are doing is we are calculating the MSE on the test data 5 times for the model 1. We are calculating MSE for the train data 5 times for the model 2. And we are averaging it out, and we are saying that MSE, which on the 5 test data averaged out, is giving me the lowest
Okay, so basically set
value
one,
is the choice.
yeah,
Is the
set
model
one
choice.
versus set two versus set three versus set four is what we are doing.
Right, 5 times. I need to add a set more also. Let's
So
because
basically,
5 times
yeah,
MSE for the set 5 for model 1. Similarly, it will be MSE for the model 2 set 5. Right, one model more I have added, and this is the 5-fold cross validation.
so basically, if we do this for five means, I mean, four, I mean, the five combinations. So it's a five-fold. If we do this for three, so it would be three-fold cross validation.
Yes, if we do it for k times, it will be a k-fold cross validation.
K-fold, okay. Okay.
Okay. So that's it. I think, yeah, any last question before I at least give you the tute, because I don't think so we'll have time to complete the tute as of now.
Sure. Yeah. No,
Any question you want to ask?
I think I'm fine.
Anybody else who would like to ask any questions? So I'll go back to the slides. This algorithm is clear to you, the boosting algorithm?
Yes.
Okay. So let me just take a 5 minutes break and I'll come back.
Okay. Sure.
Can you hear me? Are you able to hear me?
Yes, you can.
Okay. I have shared a tutorial here. Fine.
Okay.
Just have a look at it in the chat.
Yes.
So because I won't have time to complete this as of now, but I've shared that in the chat. Can you please check it out at your end?
Okay.
Okay. So let me share the screen again. This is the tute. Can you see the screen and the tute?
Yes, I just opened that tutorial and
Yes, and I also shared that in the screen.
yes.
But this is one implementation of the XG boost. You can try it out.
Okay.
Because I will take a time until half an hour to 1 hour it will take to complete it. So I've explained to you to the theory. This is a very simple tute. This is one of the variants of the boosting algorithms, which is the XG boost. This is one of the most useful and result-oriented algorithms today in the analytics world. The XG boost. Fine.
Okay.
Okay, then any questions from today's class you would like to ask?
I think I have asked enough. So I'll go through this tutorial and what we have discussed today, and maybe if I have any questions, I'll drop you a mail maybe.
Okay. Also, yeah. Also, I suggest that you join some of the competitions like Kaggle competitions to get a feel of what is happening in the field. I'm sure you're aware of Kaggle also.
I mean, we've just introduced today to this.
Okay, so have a look at Kaggle, see the computations and the data sets which are happening, and then you'll get a feel of what is happening. Okay, guys, then thanks a lot. I think we are nearly time. Thank you.
Thanks to you.
Thanks to you. Bye bye. See you.
Bye. Bye. See you.